So a lot of people want to know how you structure your lessons. How do you plan them? What do you do?
That's a big question.
Yeah.
And it's you know what I'd say? It's a similar question to, for instance, how do you cook a meal? Right? Now, I'm not an avid cook or a skilled cook, as my family will tell you, but I do at least know, like, there's an infinite number of different things you could cook, and therefore you will do things, like there's an infinite variety of ways that you would, approach that meal you're going to cook, right? So I guess the first thing to say is, how do I structure a lesson? There can't be a singular answer to that, and that's fine. But there are still some general principles that I always apply, no matter what my final lesson ends up looking like, and then that process kind of leads to the structure that, whatever that looks like, I come up with. So, where I begin with first is, here's the syllabus, right? What is the intent behind this particular dot point being in the syllabus? 3D trigonometry, right? Why do we have students learn this? Like, I know they have to be able to calculate the angle of elevation to this flagpole when you've got the angles of elevation from two other locations. So I know they have to be able to answer some kind of question, but that's actually a very superficial way of thinking about, why did we put this in here? Like, why did the syllabus and the curriculum writers think this was worth holding on to? Because in fact, I can't remember the last time I thought, here I am, out in the real world. Thank goodness I have these two people who've told me an angle of elevation. Like, that doesn't happen, right? But nonetheless, that's actually a really important concept. Why? Because what that syllabus dot point is in there to develop is a student's spatial reasoning in more than just, like, we spend so much time in 2D, students get really good at it, and then their brains like fizzle out when, even though this is the world we live in, actually reasoning there's a whole new level of cognitive load and abstract representation. Like, think about it. We're representing 3 dimensions on a page in 2. That's really hard. So I think about, what is this supposed to get to my students? And I'm already now thinking about experiences or tasks or activities that will help to feed into that. And then I'll start to think about, okay, how do I understand this concept? I'm teaching, like, we've got new courses in stage 6 at the moment, and it's got lots of ideas and topics and skills that I've not encountered before, I've not taught, or maybe I didn't even learn as a student. Continuous random variables in the Mathematics Advanced course. I didn't do any statistics at university, which I am dramatically regretting. But it's like, okay, I now want to think about, how would I understand this from a student's point of view? I want to do that work, and often what that does look like is, well, let's find some questions that students will be posed. Let's go to the textbook, let's go to exams. I'm going to start to answer these questions for myself. Think about what's hard about this idea, what's complicated here, what ideas does this connect to, right? Where is there already some foundation that I can build upon, right? And then once I've got those ideas, I'll then think, is this suitable for students to do together in groups? I always try and do that as much as I can, because I think that the physicist Richard Feynman said, you do not understand something truly until you can explain it simply. So putting them in that situation is always ideal, but you can't always do that, sometimes quite challenging. What are some helpful resources or visuals that will help me, we've been thinking about the dot product of 2 vectors in extension 1. And that can be a very mechanical, pardon the pun, process to go through. It's like, just here's a formula, just put the numbers in, you get the right answer. But what we really want is for students to get an intuition for what this even means. I calculated the scalar product, the dot product. I have a number. Why do I care about this number? How can I interpret that in the light of what these 2 vectors are, right? So then I'll go searching for metaphors and analogies that will give students an experience of that, right? So I'll do all of those things. I will think about, is this one of those lessons where I'm introducing a whole bunch of terms and ideas? You guys got to see this, actually. I did one recently where I was like, guys, we've learned all these new symbols in logic and proof, and it's just kind of like swimming around like algebra soup right now. I want you guys to have a go. I'm just going to give you some things, they all fit together, but start to see if you can connect them yourself, like it's a card sort activity, right? So it depends on the nature of what I want my students to learn, how I will then structure that. Do I do that first and have them working independently, or do I do that at the end, after I think I've explained enough and they can do this task? All these kinds of things feed into the complexity of how I might structure it. And then the last thing I would say is, I want there to be variety and rhythm within the classroom. At this school, periods are roughly 53 minutes long. That is way too long for any human being to do a single thing. They have to stop, they have to pause. They have to have moments to listen, have moments to speak, have moments to work together, and then other moments to say, actually, talking to you would really interrupt my brain right now. I need to have a go at this independently. And so having that sort of spaced out throughout my lessons is also really important.
I've been told that teachers don't be surprised when you have boring lessons, because sometimes that just happens and you actually need those. What do your boring lessons involve? Like, what do you do? You're like, I don't have any.
That's not what I'm going to say. I do have boring lessons. Every teacher does. So I'll come back to that idea in a second. But I do want to push back on the premise of the question. It's very well intentioned. I think what people mean when they say that is, do not plan every single one of your lessons as a kind of like, this is gonna blow their minds apart, like I'm gonna spend like 3 hours like cutting things apart and then they're going to like put this together in some jigsaw puzzle, it's gonna be amazing. The reason why teachers want to caution you against doing that is because you will die in your first year of teaching if you sacrifice the sleep and mental well-being to try and make every single one of your lessons like that. I routinely remember spending like 3 to 4 hours planning a single lesson when I was on prac. The average teacher is going to teach something like, I did this number crunching the other day. It's going to be about 15 hours a week. Sorry, no, I take that back. It's about 20 hours a week, face-to-face teaching, right? So if there was let's just be conservative, a 3-to-1 ratio, right, of planning to lesson time, right? 60 hours just to plan. We haven't even talked about marking and writing assessments and that kind of thing. Real actual thing, you'll burn out. And many teachers do in those first few years. Some of our best teachers do because they have the highest standards for themselves. So that's what's sort of underneath that advice. But I would push on that because I think eventually we want to get to a point where none of our lessons is boring. That actually in the kernel of every single lesson that you give, there's something that makes your students curious, surprised, excited, and wanting to find out what happens next. I think that degree will vary. One of my favorites is that this used to not be in the course, but within Extension 2 Complex Numbers, there's this thing called Euler's identity. And it's this wonderfully beautiful mathematical object, and I would work up to that. And that's like an a Mount Everest experience in mathematics. That's not going to happen every day. But even when, like I said, I was talking about the dot product of two vectors before. Even in something as somewhat dry and mechanical as that, I think it is important for students to feel a sense of, I can do this. I've just developed a new skill. That's exciting. Everyone loves to develop in their mastery. Or, wow, that gives me, I can see that's going to connect to, maybe I want to be an engineer one day, and this is going to help me understand how shear forces of wind on a building work. And that's really complicated to work out. This has just given me, a foundation for that. I think every lesson's got to look a little bit like that. But I will say, I've been teaching for almost 15 years now, and there will still be lessons that I come out of and I'm like, not super satisfied with that lesson. It's often when a concept is still new to me and I haven't developed a good grip on it yet. And maybe it looks like this, guys, this is in the syllabus. I don't know a really good real-world application to this yet. I do not know some kind of cool and surprising and counterintuitive result that flows out of this. I'm gonna have to research that. I'm sure I can find one, I just don't have one yet, right? All this lesson that we're gonna do is, I'm gonna show you how it works so that this skill that I've developed, you'll have. You'll leave this classroom, you'll have learnt that. That's where I have to be content. And sometimes that'll mean, okay, follow this example, guys. Now have a go at practicing it in a textbook. I'm not ashamed that I do that sometimes, because sometimes that's a foundation for a future lesson. But I do want to try and minimize those as much as I can.